Okay, our next speaker is Victoria Stodden, who comes to us from Columbia University, where she's an assistant professor of statistics.
Okay, my mic's working. Great.
It was that Macintosh. The Macintosh corrupted the whole thing.
Oh. I want to see it too. Here. Okay. That's fine. This is fine. That's fine. We need. Can you do the full screen here so we don't have that?
Yeah, we can.
Okay. Great. Well, thank you. I love the idea of having this discussion today about primarily around the OSTP memo, because it brings out so many issues that you can just see by how full the room is that are on so many people's minds. And I'm very honored to be a part of this and talking to you today. So in thinking about what the OSTP memo says about data and open access to data, I think there are two ways to two sort of lenses to look at this, and that's what I'm going to try and bring out through my talk. So two parts. So first of all, I'm going to discuss, well, what does the OSTP mandate really mean? And what's their lens and the government lens for thinking about open access to data? And then in the second part, I want to talk about what the implementation means, what I would call our lens as research scientists and community members creating the data, and how those two actually differ and what we should do about it and how important this actually is. So I think for the implementation, there are lots of opportunities that are opened through the OSTP memo, and then of course there are challenges and caveats coming through the fact that government has a slightly different lens on how they view open access to data. So I warn you on the next two slides. What I did is condense the information in the OSTP memo so that we know exactly what it's saying and exactly what we're talking about. So by the way, my slides are on my website if you prefer to sort of follow along on your laptop. So data in the memorandum. So digitally formatted data arising from federal grants should be stored and publicly accessible to search, retrieve, and analyze. And as people noted this morning, this is the first discussion of data mining and retrieval and these sort of overlay technologies on digital scholarly objects. And this applies to the data as well. And then here's a quote from the memo. Data is defined as the digital recorded factual material commonly accepted in the scientific community as necessary to validate research findings, including data sets used to support scholarly publications. So this to me has a lot of import in there, and I want to particularly point out the word validate that they've used. So part of the rationale in the text here is that data is important to validate research findings. So this came out in the discussions this morning, almost seems obvious, but I think this is a really important guiding principle embedded in the OSTP memo that we can really use to really bring some benefit to the scientific community from this. Okay, so bear with me with all the text. So here's the condensed version of what they say. The part A here is the most important part, and you don't need to read it, I'll just step you through it. Part A, maximize access by the general public and without charge to digitally formatted scientific data created with federal funds, with caveats about privacy, confidentiality, and IP, and so on. So that's the guiding principle in the OSTP memo. And then there's a little more information if we look at the other requirements that are laid out in the memo. So part B, ensure that all researchers receiving federal grants develop data management plans describing how they're going to provide for long-term preservation of and access to scientific data. As many people in the room know, since the beginning of 2011, NSF has required data management plans with every new grant, and they go to peer review. And there was no real directive about what you needed to say in your data management plan. You would just sort of say how you're going to manage data. So this is a departure because this is starting to talk about access specifically, preservation specifically. C, it seems like this is really information for the federal funding agencies that you're allowed to include costs to do this in your application for a research grant. D is important, but in a sense already takes place. Ensure appropriate evaluation of the merits of submitted data plans. I imagine this would be implemented as it is now, which is it devolves to peer review on the panels evaluating the grants. E is important and new. Include mechanisms to ensure that intramural and extramural researchers, so inside government and federal agencies and outside, for example, in institutions, comply with data management plans and policies. There's no real enforcement mechanism. In such a short talk, I don't have time to go into the grant guidelines, but NSF, NIH, and federal agencies have had grant guidelines either mandating or encouraging data and code to be made available. And this goes back to 2005, 2003, and the enforcement is missing. So I think E is crucial in how this actually comes to have an impact on how we communicate our data and our scholarly research. Okay, the last busy word slide. Promoting the deposit of data in publicly accessible databases, so use the repos that are already out there. Encourage cooperation with the private sector to improve data access and compatibility through the formation of public-private partnerships. So this one, it strikes me as odd. Earlier in the OSTP memo, it talks a lot about publishers, particularly around open access, but it talks about, like we heard this morning, that they're important and part of the process and so on. And I think this is something of a nod to the role of publishers in here. I think this also speaks to this other framing that comes from the fact that this is something from Washington. It's not something that's emergent from the research community. If you read the preamble of the memo, it talks about the rationale behind this being maximizing the impact of federally funded research, i.e. through commercialization or through a new innovation for companies, through economic growth, through entrepreneurship. All these things that we know as scientists are important as downstream events that happen from our research. I mean, we're all hoping to impact society and improve society and so on. But this sort of commercialization aspect is front and center in the preamble of the executive memorandum. So what that says to me is that this is something, they're speaking to Congress members, they're speaking to their constituents, and this is the language they use to couch open access. As I'll get to in a moment, this is very different from the language that I would use, say, for example, speaking to this room to try and persuade you that data access is a good idea. Develop approaches for identifying and providing appropriate attribution for data. This is something that I think is incredibly important and is evolving within the scientific community. I think it's very important that it's in there. In coordination with other agencies and private sectors, support workforce development. Okay, and then the last one, provide for the assessment of long-term needs for preservation of scientific data. So a couple of interesting things. They don't, as we heard this morning in the memorandum, they specifically say there's no additional funds for this. This all needs to be funded through already allocated resources within the federal agencies. And this notion of this long-term preservation and building these structures, which I imagine will be built for long-term data access, stewardship, curation, is this is a huge time span of project, and it's going to be really expensive, and we'll see what happens there. But I think this is something where it's a little bit wishful thinking that that's something that can be done within existing resources. So I think we're embarking on a very big challenge with open access to data. Okay, so that's my take on the memo itself. Now, that needs to be implemented, as we heard this morning, through the 6 months that federal agencies have to develop their plans and submit it to OMB, which is coming up next month, and then they'll be reconciled in August. So let's see how a scientist might confront this problem with open access to data. Would they have come up with the same guidelines, or would they have come up with something different, thinking from the scientific community, and how might they have done it? So here's what I think. So I don't think anyone in this room would argue that open data is absolutely crucial to science. I put today in the title, but in a sense, it's always been crucial to scientific discovery. It's not a new concept. So this is something that comes from this notion of skepticism that's embedded in how we do scientific discovery. And this is a photo here of Robert Boyle in the 1660s, one of, we heard this morning, Francis Bacon, and founding the notion of the scientific journal. And Robert Boyle was involved in those discussions. And he brought in this notion of reproducibility. So guidelines about what is appropriate for scholarly dissemination. And so it's about this notion of knowledge transfer, it's about transparency, it's about telling other people how you got to your results so that they can be very skeptical about what you've done, not telling people the answer. I mean, that's not at all what science is about. So really what a scientist wants to do in some abstract sense is perfect the scholarly record. And our scholarly dissemination is really about getting the scholarly record as best as we can. And as we heard this morning, it's never actually perfect. And then we heard lots of issues in how we actually implement that, but that's the grand goal. And to me as a scientist, that's really the driving impetus around how we construct our scholarly dissemination. Now, technology, of course, in the last 10, 20 years has radically changed how we do experimentation. It's changed the notion of even what we mean by data. And of course, it's changing and has changed communication. So now how do we reconcile those changes with all these principles that I just laid out? So let me give you an example of how impactful technology is. So I have three sources of impact here. The first one, there's been a lot of discussion about, I'm sure folks are familiar, huge amounts of data that we're confronting there. Data is becoming pervasive in all sorts of fields that weren't traditionally computational or empirical, and in huge amounts. So just one of the 5 projects at the Large Hadron Collider, I'm told is producing, when the collider's up and running, 780 terabytes a year. That's not something where, you think of it in the context of the OSTP memo, yes, the problem with access there is not in goodwill. I mean, there are real barriers just in the sheer size of the data. If you scale down a bit, the Sloan Digital Sky Survey in 2012, they had their 9th release. It's a mere 60 terabytes. Again, this isn't something where you just sort of were going to download and click around on your laptop. There's an entire infrastructure that needs to exist around this data to make it useful. In 2009, there was an article in Science talking about the quantitative revolution in the social sciences and sociology, political science, economics around social network data, and how it had transformed much of the social sciences now to really a computational field. In a survey in Science in 2011, out of 1,700 researchers, 340 working regularly with data sets over 100 gigs, 119 regularly working with data sets greater than a terabyte. I mean, this is really serious stuff that's transformed the tools and infrastructure and the communication that needs to go with that type of science. So that one I think people probably are familiar with, and I think the OSTP is familiar with this, and I think this probably undergirds some of their reasoning behind the memorandum. There's 2 other deep impacts that I think are less well known. The second one is the increasing in computer power. So this isn't about storage, it isn't about sensors, it isn't about data collection, but it's about just this massive high performance computing that we have. So now we are able to do things like ask questions about the evolution of physical systems and do full simulations, rerun the simulation, change the parameters, and ask questions and get answers that we never could have 20 years ago. And this is also a new method of scientific investigation, bringing with it new ways that we need to communicate the results to be consistent with Francis Bacon and Robert Boyle back from the 1660s. If you agree with their principles, which I do. The third one that almost nobody talks about, which I think is just as important as the first 2, is that now with the computational pervasiveness in science, deep, fundamental, bona fide scientific contributions are happening in software and only in the software. And I'm a statistician, and I could point to like a trillion examples of algorithmic improvements, analysis improvements, modeling improvements that are happening in software. And there are papers that write it up and so on. But really, if you're not looking at the code and looking at what's happened, you're not really understanding what's going on. So that's about understanding. The corollary, of course, is implementation. So if you don't have access to the software, you're not applying it to your data or someone else's, and you're not extending it into answering new questions in new areas. So I think these three are equally as important when it comes to dissemination and when it comes to open access. Of course, the memorandum talks about publications, talks about the first one. Okay, the other thing that I want you to think about is that without the data, without the software, we are engendering this credibility crisis in the publication of computational science. So I looked at the Journal of the American Statistical Association, one of our flagship journals in statistics, and I went back to 1996, and I was curious as to how many of those articles were computational. Like, are we really becoming as computational as what it seems? In those days, about half were computational, the rest were mathematical proofs. None of the computational articles told me where I could get the code or the scripts that produced those results in that paper. If you fast forward only to 2009, like 4 years ago, all of them were computational by then, and it stayed constant that way. I mean, there can still be mathematical proofs, but they'll have a simulation or an example or an implementation or something that's computational in the paper. And then 2011, we're up to about 21%. This was a low bar. Like, I counted you in trying to make your code available. If you even just kind of mentioned where it could be or something that recognized that this was really important, getting access to the scripts or the software. 21%, of course, is infinitely better than 0, but miserable, right? And if you think about the importance of the code, as I just explained, to understanding what those results really mean and interpreting them, and 4 out of 5 papers, it's just opaque, that's a real problem. And so this is what I think is causing a credibility crisis. And Ioannidis has an article published in 2011 where 9% of the authors he looked at were making their data available. So it's around the same order of miserableness. Okay, so here's a scientific perspective. So an emeritus professor in the geophysics department here, John Claerbout, more than 20 years ago pioneered this notion of what he called really reproducible research. And there's a nice quote paraphrasing his take on this by my advisor, David Donahoe, who's in the statistics department here, where he says, the idea is an article about computational science in a scientific publication is not the scholarship itself. It's merely advertising of the scholarship. The actual scholarship is the complete set of instructions and data that generated the figures. How do you get the data or the set of instructions? You don't. So there's this argument to be made that we're facing this need to update the scientific method. You've probably heard in keynotes, grant proposals, sort of foreign policy pieces, lots of chatter about the third branch of the scientific method and simulations and computation, the fourth branch, our data deluge. So if we think about how we got these branches and where they came from and what they really mean. So the first branch of the scientific method, deduction, complete deductive systems such as mathematics or logic, insufficient to deal with observational data. So we have the second branch, the empirical branch of the scientific method, which has statistical analyses of controlled experiments. And then branch 3, branch 4 around big computation and big data. So the first and second branch are hundreds of years old, and they've had a long time to think about what it really means to communicate a scientific finding for each of those branches. In the deductive branch, they have a well-defined concept of the proof. I mean, obviously, you're not going to try and publish a mathematical result without providing a proof so that people can understand why your result is right, or use skepticism and poke holes in it, and so on. In the empirical branch, also they've had hundreds of years to come up with a well-defined machinery of hypothesis testing, a structured way that they communicate results with a method section so that you can tell other people exactly how you did it. In these observational sciences, the notion of a lab notebook is built in from early days of training, so you can track everything you've done, report it to other people who are trying to evaluate and understand your work, and just make it more widely available. This hasn't translated over to computational work. So this notion of a lab notebook, you go through this precise documentation of your work at the bench put it in Excel and start clicking around, and then there's no trace about what's happening, and then so this thinking, this sort of very careful thinking about communicating results and about reproducibility needs to translate into the computational sphere and how we do computational science. And the argument is that computational science as practiced today doesn't generate reliable knowledge. It doesn't rise to the level of a third or fourth branch of the scientific method until we get these same standards of communication in place, until we are able to get a hold of the data, get a hold of the scripts, and follow through those steps and instructions from the data that produce the published results. So openness in science. So here are some ways that I've been thinking about it. So I think scientific policy needs to support scientific ends. So when I see something like at the beginning of the OSTP memo where they talk about economic growth and they talk about entrepreneurship, all of which are important, laudable goals, but it's not our purpose, right, as scientists producing scientific research. Those are sort of downstream second order impacts. Reliability, accuracy of the scientific method, that's what we're trying to do. So facilitating reproducibility is extremely important, and part of that, the ability to regenerate the published computational results, given the data in code, alongside the published results itself. You don't have untethered results just sitting out there in a vacuum. That is what we have today, but that's not what we should have cognitively. So my argument is we need infrastructure to facilitate deposit curation of data and code. OSTP memo talks about data, doesn't seem to notice that those methods are really important and part of framing and structuring scholarly communication going forward. Link this to the published results. Don't have results out there untethered without a way to understand what they really mean, the computational results. Similarly, don't have software data code just sort of floating out there untethered to results that it underlies. And then, and the memo does do this, think about this permanence of this link and how this persists into the future. These are all, I think, still open questions, and I think that the scientific community will solve most of these, I think. So we heard in Myron's talk this morning when he had that slide with scope written on the top, and he talked about how difficult it is to understand what it really means to share data. And I think he said something like, it's sort of well known in publications about sharing, it's not anywhere near as well known in data. I don't think he's right, because I think we know a lot about sharing data from these guidelines about what it means to do scientific research. I think if we use something like being able to regenerate the results, data is shared, if it's information that's needed to replicate the published results, that's a way of scoping and understanding what data we share. If we just say, like they do in the memo, data, then that's a very difficult word to understand what that means in terms of what we should actually share. Like, do I collect data, then it has to go out there? Or is this something that is post-publication? So I think in interpreting the OSTP memo, we need to really hinge a lot of it on its use of the word data to validate published results and use that to scope the discussion of what needs to be shared and curated and communicated more broadly. And by the way, the 6 months embargo and all that discussion this morning, that was applied to the publications aspect of the memo. There isn't the similar directive for data, and I think that's important, and we should be right on that and get data and code out there with the publication and make sure that this is disseminated as quickly as possible. Okay, the other point that I wanted to make is I think that this is something where the way that we're doing research really needs to change. I think it's very difficult to just sort of talk to an author, you know, that paper you published a couple of years ago, could I get the code and the data with it? If it's not something that you've thought about from the beginning when you start your research process and you're going to go through to publication, it's extremely difficult to share that code and data. So we need infrastructure and tools with foresight about sharing data and code during the research process, allowing us to save what's important and get things ready to be out there and shared publicly. The other point that I wanted to make is that also using this word data very loosely, it means very different things to different researchers in different areas of science. So we have a whole spectrum of data-driven research where really it's about the instrumentation. And once you sort of have the readings, that's most of the science is done, and you publish kind of almost what your eyeball sees in there. And then we also have empirical work where the data may be empirically collected, maybe similarly through instrumentation or through other forms of collection, but there's a lot of analysis and inference that happens on the data. And then it goes right through to research that is wholly software, simulation-based research, and it produces data. So for people in scientific computing, when you start talking about data, they think of it as an output from what they've done. And I think this sensitivity to what it means to share data, share code, what reproducibility means for different research questions and in different contexts is very important to this going forward. Okay, I'll point out a couple of things just before I wrap up. There's a National Academy's data sharing report sharing publication-related data and materials, responsibilities of authorship in the life sciences. And they have principle 1. Authors should include in their publications the data, algorithms, or other information that is central or integral to the publication. That is, whatever is necessary to support the major claims of the paper and would enable one skilled in the art to verify or replicate the claims. And so I also want you to notice the year, 2003, right? So this report is published, and these are old ideas that we've been talking about for a long time. We're not the only ones to notice this, so I was very interested in what journals are doing about this. They're really the gateway to how we do this scientific communication. So I looked at 170 journals, and this paper has just come out in PLOS One last Friday. So take that, Mike. So what I did is I looked at what were the requirements about data and about code in 2011 and then in 2012 for 170 journals. And you can see that it's still a minority that have these policies, but there are lots that have these policies, and it goes from about in 2011, that's about 33% that have some kind of data sharing policy. And then in 2012, it goes to about 38%. So that's, a pretty big, that's about 20-25% increase just in a year. And so this is something I think the journals are engaging with and taking very seriously. And I think there are real opportunities to move with the journals as well as the funding agencies here. Okay, and then I wanted to put up also a very incomplete table about tools that are being developed to help, especially with the type of research and during the research process. So I think much of the solution will actually come from the development of appropriate tools to do reproducible science. I grouped these into 3 very loose and overlapping categories, like dissemination platforms that link up code and data and allow you to reproduce your results, ones that are pre-publication, workflow, and workflow tracking and research environments that really help you save and curate data and code as you're going, and ones that we've heard a little bit about it this morning, embedded publishing, verifiable computational research, and also the share package and so on else that we talked about the last one. And this is my last slide, and it's a blizzard of words you're not necessarily meant to read. But what I wanted to point out to you is this is not something, the OSTP memo is not something that has hit us out of the blue. This is something where many different communities across the entire landscape of scientific research have been talking about issues around the credibility crisis, around reproducible research, around sharing data, sharing code. And you can just sort of, maybe you can't see, but I'll point out some. You can see that there's mathematics and computer science, there's bioinformatics on here. AAAS did a session in 2011. There's law schools, computational science and engineering, and people are using words like reproducibility. There's a lot of grassroots movement here to capitalize on this. And I think that in solving these reproducibility problems, the OSTP memo is most important in breaking this collective action problem. It takes work to curate and share data and code that's largely unrewarded, as that big discussion right before lunch let us know. And for one person, I mean, everyone may agree with this, but for one person to kind of move forward and take that burden on is really tough. So the OSTP memo, my hope is that it helps to push us all towards data sharing and code sharing, and minimize that collective action problem that we're stuck in and move us to sort of a new equilibrium, regardless of their interpretations around how we should or should be doing it or what. I think the implementation is really up to us, and I think we know why we're doing this and what we need to do to move to reproducible computational science. So thank you.
Thank you very much, Victoria. Do we have time for a couple of questions?
I question two of the negatives, maybe three. One is privacy security. Two is simplicity of reproduction. Privacy security says a lot of the data out there, if it's not properly sifted, is terribly intrusive of my privacy. And I don't know if you really have the data, how you can preserve the privacy if it's open. Second part is the simplicity. If you publish, give me the data and the software, it's very easy, maybe too easy, for me to take the data, run the software, and reproduce. If you don't, if you tell me you've gone and taken surveys and run statistical analysis, then my reproduction is going to be harder because I'm going to have to do other surveys, write other programs, and thus do a really independent reproduction. So I worry about those two.
No, I think those are great questions. So the first one, I don't have any silver bullet around confidentiality either. I think that's something where there's certain confidential data that's not going to be shared, and it's not going to be shared, and that's the only way around it. And I think we can be innovative around how we do that, in that if there are, say, consortia of researchers, say maybe 5 institutions are involved in a particular research problem, maybe they can sort of share within themselves to try and sort of mimic a reproducible research kind of environment. But really, special things have to be done around confidential data. I don't see that becoming open. Especially IRBs are very, very conservative about sharing data and privacy and confidentiality, and that's pretty much a barrier to any kind of open access to data. With your second point, no, that's exceptionally important. So I think that this notion of being able to take someone's data and code and easily, I would love it to be easy, easily replicate their findings. I agree with you that's not a scientific contribution. I agree with you if I go and I really reproduce the experiment, like recollect the surveys and redo the analysis and recode it, and then I get their results. Now that's a real scientific contribution because it bolsters those findings, because it's independent. But now, suppose I go through and I reproduce those, like I go through and I do the surveys again, I recode this and I get something different, which I guarantee you is what's going to happen. How do we know what the differences are if I can't get into the original code and data and really understand what the steps and process were that led to it? I agree, hitting return, no scientific contribution there, but I don't think that would obviate independent replication of the experiments, but it certainly will, when there is independent replication of the experiments, allow us to figure out why they differ and reconcile those results, which is incredibly important. So I think we need both, is the answer.
One more question? Okay, then we'll stop there. Thank you.